So you have the velocity vector, and you have the path going right back to the origin, but that is not the acceleration. But I just want to have that in there to show you what's going on. And I'm going to even exaggerate a little bit more to make the elliptical path of the satellite look like this.
Alright.
Okay? So the first thing I want to do is just kind of zoom in so that you can see what's going on with that path back to the origin. So what do you notice about this line as we move around the ellipse as drawn by the Desmos program now? This is the path going back to the origin.
It's sort of, it's speeding up and then slowing down. It's going counterclockwise, and it's like speeding up and then slowing down again.
It's not actually that. No, the speeding up isn't actually that noticeable this far in.
So it's interesting. Is it speeding up or is it not speeding up?
I actually don't think.
What do you think looking at it here?
Well, I don't think.
What do you think?
I think it looks like it is speeding up.
What do you think?
I don't think it is. I think the velocity is definitely changing, but I don't think this is changing.
Yeah.
Yeah, get it. Bring the metronome over. Alright, while we're getting the metronome, we have... Okay,
Alright.
let's see. So try to see if you can set the metronome. So do you think that line is speeding up and slowing down? Or
It's not. It's actually staying the same.
Okay, so our angle that we're moving around is actually constant here. But if I zoom out now, what's happening to the particle going around the ellipse?
The particle itself is speeding up. The velocity.
Okay. How can you tell that the velocity is increasing?
Well, this red line that represents the velocity
getting longer
gets
and
longer
shorter.
over here and then gets short back over there.
Okay, yeah, and so from here you can turn the metronome off. From here, it actually does, it's harder to see that the angular velocity is constant because the particle itself is moving faster and slower. And so if this is the Earth and this is a satellite moving, or like if this is the sun and this is a comet going around, is this what the motion looks like?
Well, not quite.
Okay, what do you think before we get into what might not be right here about the motion? What do you think? What do you think is going to happen with a comet when it's orbiting around the sun, or a satellite when it's orbiting around the Earth?
Well, I think it might go faster as it approaches, as it gets closer to the sun or the Earth.
Okay.
It's not, the gravitational pull is going to get less and less as it goes farther away, so it should slow down over here and then get faster.
All right. So what do you think?
Yeah, because the gravity acts more on something when it's closer. So I think, like when the comet would be in here, it just gets slingshotted around and then slows down, then comes back in.
Okay.
So I think this would be kind of like the reverse of this.
Right. So our graph here is showing like constant angular momentum, like the hands of a clock spinning around, gets it exactly backwards. And we have to understand what it looks like. So it's more than just the path. This is the right path. But our simple idea from parametric equations of just taking the derivative of the angle or keeping the angle constant is wrong. There's a little bit more to it than that. But nonetheless, what I want to show you next are some relationships between what some of the planet orbits look like, so you can actually see them.
All right.
Okay? So we'll go to the last video for that.